up to now, we have been using a lossless simplified solution for our calculations. This is quite routinely used. It gives you a first design, and then if you have to actually model your losses because you have a long transmission line, or you need to calculate accurately what is the loss included in the line, you have actually to use the more general expressions and calculate to take into account the resistive and the conductance of your dielectric, your losses in general in your transmission line into account. And this is what this slide describes. Actually, losses either in the conductors or the dielectric or all together results into a propagation constant. We have, instead of being a pure imaginary number, it has a real part. It becomes a complex parameter. And the real part of this parameter, which is this alpha parameter here, actually models the attenuation of the line. And you see here the phase which is actually lost by the wave when propagating along the line is described by this beta parameter. We have been using this parameter in our previous calculations, but then if we have to include the losses, we have to include this this real exponential parameter, which is also modifying slightly the propagation constant. And the role of this parameter is just an exponential decay, an exponential decay term along the line. And okay, that's not a problem. You can compute what is the drop-off voltage in your transmission line. You know the length of the line, you have the alpha parameter, so if you have an input voltage here, the output voltage will be lower depending on this alpha parameter and the length of the transmission line. This alpha parameter is expressed in Nepers per meter, which is an exponential constant, decay constant of the transmission line. When you multiply by the length, you have the attenuation in Nepers, which is the natural logarithm between the input and output voltages. Nepers are very straightforward to calculate from the constants of the line, but it's not very practical parameter. So most engineers will use attenuation in dBs, in decibels per meter in this case. So, but it's not a problem. If you take logarithms, you can transform this alpha parameter in Nepers per meter in a dB per meter parameter. You have to multiply by this constant 8.68. In such a way, you know what is the power decay of your transmission line at the end. This is just the ratio in logarithm units, in dBs per meter units, relating power or relating voltages along the line. Now, let's to finalize this lecture on transmission lines, let's take a look on the transients. So transmission lines can be used and are routinely used to actually deliver signals, sinusoidal signals, for example, power supply, 50 or 60 Hertz, or radio frequency applications, or many applications you can just model. We are just transmitting sinusoidal signals. Also in audio applications, you can take a look at the spectrum of the audio, and each line of the spectrum corresponds to a sinusoidal signal if you want. But there are certain situations when this sinusoidal analysis is not the most convenient to do it. So let's assume we use a transmission line to connect two digital systems, and they are just transmitting pulses. So let's, for example, we connect two chips, and these chips are actually communicating digital levels, ones and zeros, for example, with two different voltages. So now the typical signal here is not a sinusoidal, it's a rectangular pulse. So if, for example, a bit is a rectangular pulse with actually delivering an information of 1 and dropping this pulse to a 0, it's for example, a bit 0 in a digital communication system, for example. Now, what is the behavior of the transmission line when it is used to actually communicate with digital signals to two or more different devices, for example, in a network, in a digital network of computers? Again, we have the same properties we have been studying up to now are actually valid in this case, of course. So if everything is matched, for example, in this case, so generator or transmission line and the end, everything is at the same impedance, so there's no reflection, so the pulses will just travel as you would expect, ideally, from the source towards your whatever you have here, a disk or a computer or network of computers, whatever. So no reflections, no back and forth of pulses here traveling around the line, and that's the desired situation. But what would happen if we have a not match condition here? What would be the evolution of the signal? That is important to study in certain applications. So let's start for the ideal condition. There's no reflection, everything is perfectly matched, everything is at the same impedance. So if we connect this generator here, this generator has a voltage of B0, we switch this on at a certain time, t equal to 0, what's going to happen? Well, at the moment we switch here, if we measure the voltage at the input of the transmission line, this voltage will be V0 divided by 2, not V0. Why? Why is that? Well, we have a characteristic impedance of our generator, and we have a transmission line which behaves as a load of Z0, or of a certain real resistance parameter. So we have here, what we have here is a voltage divider. Z0 is loaded by Z0, so at this point we have the voltage of the generator divided by 2. That is what we have here. But that is just at the instant of when we switch on at this point, at the input point. At the output of the line, this pulse has not arrived yet. Remember, we have a delay, a propagation delay at a certain speed, but we can compute the BP parameter that we computed before. But after some time, this electric field here progresses along the transmission line. So you see here this rising edge from 0 to B0 divided by 2 actually is progressing along the z-axis of the transmission line, and at certain time the rising edge will arrive at the end of the line, and then what will happen here? There's no reflection, it's perfect match, so no reflection wave will appear, so that will be the end of the story. So this will stay everything at B0 divided by 2 forever, okay? If you, for example, take out the transmission line and you connect the load directly to the generator, at this point you will have this steady state solution, B0 divided by 2, okay? So that's a simple case, everything is matched, the pulse rising edge of this pole progresses around the line, and if the pulse does not return to 0, that is the situation, the steady situation forever. Now, let's go into complicated things. Let's make a complete reflection, let's make a short circuit at the end of the line. So assume we have a problem of this line, and at a certain point is short-circuited. What's going to happen in this case? Well, at the beginning is the same as before. When we switch the connection here, we switch on the connection of the generator in the line, actually we have this V0 divided by 2 voltage, which is progressing around the line. Nothing happens, nothing strange happens until we reach the end. When we reach the end, this is a total reflection. The reflection coefficient in this case is -1. This means that the backward signal is having opposite voltage compared to the forward excitation. So actually, when the backward progresses towards the input, is actually cancelling this negative backward signal propagating, is cancelling progressively towards the left until reaching the generator. When this left reflection reaches the generator, everything from this point to the right will be at 0. So the steady state of the whole transmission line, when time has evolved enough time in order to have the reflection coming towards the input of the line, the whole voltage of the line is 0. That's a steady state, which is natural because when the delay disappears, everything is short-circuited here. What will happen if we have a total reflection, and in this case provided by an open circuit? Well, if the end is just cut here at the end, there's nothing connecting the end of the line, again, the beginning is exactly the same. we have a rising edge of V0 divided by 2 progressing towards the right. Nothing happens until we reach the end. When we have our total reflection, now we have a backward signal progressing towards the input with a voltage which is exactly the same as the previous one. No change of sign, so both forward and backward, they reinforce together, and from V0 divided by 2 we jump into V0, the original voltage or the internal voltage of the generator. So this progresses now towards the input of the line. When it reaches the input port, the situation becomes steady, and all the voltage along the line is in this case V0. Okay? So we start with V0 divided by 2, and the reflection actually makes a jump which is progressively propagates towards the generator until we reach V0 steady state in this case. What happens here is all the line has been actually polarized with the voltage of the generators. There's no dissipation, there's no drop of voltage in this case. Now, let's take a further example, a more complicated one, when we have mismatches both at the input and output ports of the transmission line. So what we have here is a generator, in this case a 50 ohm internal impedance. We have a transmission line which is a different characteristic impedance, 100 ohms. And the termination is different, again, from the previous two. It's a 200 ohms impedance termination. Now, in this case, if you compute reflections at the input and output ports, we have mismatches here at the input and the output. These are the reflection coefficients. At the output is 1/3, if you compute from the previous expressions, positive. And the input, we have a mismatch. 50 and 100 are not the same impedance, so we have a mismatch here at the input. The reflection of a backward wave progressing towards the input will be -1/3, because the termination load is below the characteristic impedance of the line. So we have to take this into account. So let's see what happens in this case. When we switch this connection, we switch on here the connection of the generator with respect to the line. We have here again a voltage divider situation. We have 50 ohms and 100 ohms of the impedance. If we solve this voltage dividing situation, we have an 8-volt excitation at the input of the line. This is the first thing that happens. We have an 8-volt rising edge at the beginning of the line that progresses towards the right. At the moment, nothing happens, just an 8-volt positive edge, which is being transmitted towards the end. But then we reach the end, and at the end we have a mismatch, which is +1/3. So this means a backward wave. We have in this case an amplitude of 8/3 of volt is progressing towards the input port of the line and being added to the previous 8-volt forward wave or forward pulse. So if you add these two voltages, when this reaches the input port is not at 8 volt, it's at 10.67 volt at this time. But that's not the end of the story, because when the backward wave reaches the input port, we have a mismatch. We have this coefficient which is not 0. So this backward wave is going to be reflected again in the forward direction towards the load. Okay, what is the reflection coefficient? In this case is -1/3. Okay, we apply this constant to the excitation of the backward wave, and we have a forward with this -8/9 of volt, which is being added to the previous two. If you add these two values, at the end, when this gets the final load of at the output port, we have again another reflection. Now we have a -8 divided by 27 volts, negative. This is added to the previous voltage of 10.67. So when this second order reflection reaches the input, now we have a negative correction from the previous 10.6 volt, and now we are at 9.48. Okay? So again, the story will be repeated. This is a very small excitation now, but it's going to be reflected, going forward, backward, again, forward and backward. The amplitude of the corrections you see here every time is being multiplied by 1/3, so it's dropping. And after infinite back and forth, forward and backward returns of these reflections, you would reach a steady state which is just 9.6 volt. And how can we calculate quickly this steady state? That's very easy. At the end, if you wait for a long time, the delay introduced by this line, it can be neglected. So you can connect directly the output load into the generator, and this is just the voltage divider of 50 and 200 ohms input and output impedance. So now I'm neglecting totally the presence of the line. The line is important here in the first transients, but when these transients are going to disappear after some time, and at the end you have just the voltage divided of the two real impedance. Here you have input and output impedance. So that's the steady state situation. So if you work with digital systems and communication between computers or digital devices, you have to be careful. So sometimes you see, for example, connections between these or high-speed devices that are terminated by resistors. The reason for that is to avoid these undesirable situations, transients, which are just going back and forth, and this actually can provide errors, transmission errors between digital systems. That's the end of the transmission line block of lectures, and just to end, just a couple of references to very well-known books: Microwave Engineering by David Pothar, and Fields and Waves in Communication Systems by Ramo, Winery, and Van Dusser. Excellent books that are the reference material recommended for this block of lectures. Thank you very much for your attention.